Welcome to Part 3 of Using Response Surfaces in DesignXplorer. In Part 2, I discussed min-max search, goodness of fit, and response chart results. This video will continue with the same project, now focusing on how to interpret response surface sensitivity results. There are two different sensitivity results available for response surfaces: the local sensitivity curves chart and the local sensitivity chart. These charts are local in the sense that they show sensitivity values local to the current response point. The local sensitivity curves chart uses multiple curves to show local sensitivities. In addition to showing an input's impact on one or more selected outputs, it also shows the impact on all the other inputs. For the ANSYS range, I can pick Use Curves Data or use min-max of the output parameter. I'll use the min-max. I have the option of viewing this chart for either one or two outputs. To start, I'm going to look at the impact of all inputs on a single output, safety factor minimum. The chart shows two curves with high sensitivity, one with low sensitivity, and one that is neutral. The black squares represent the current response point for that curve. In this version, all of the inputs have a central value in the response point definition, that is, a value of 0.0 on the x-axis, so all the squares are lined up. When you vary the input values, the squares no longer match and become visible. The ends of the curve on the x-axis indicate the lower and upper bounds of its range, while the angle of the curve indicates the rate of variation. When I move the slider for an input, say for thickness, the curves for all the other inputs are adjusted accordingly. I can also view this chart for two outputs. Now, each curve shows the impact of each input on both outputs. The circle at the end of each curve indicates the beginning of the curve, that is, the lower bound of the input. The black square is the current value of that input. The slope of the curve indicates the rate of increase for both outputs. In some curves, note that the rate of variation is not constant. The curve may rise steeply, then level out a little, and then get steeper again. If a sensitivity curve has a flat spot for an input, it would mean that the variations in that input would cause less variation in the output. In other words, the design would be more robust at that value of the input. The local sensitivity chart is built from the intermediate results shown in the local sensitivity curves chart. This chart shows the sensitivity across the range, with each input represented in the same color used in the local sensitivity curves chart. Sensitivities are shown for both outputs at the same time, so I can see them all at a glance. Here, for the safety factor minimum output, I can see that thickness and depth are both positively correlated with direct impact. This chart uses bar height instead of slope to indicate sensitivity. Here, you can see that thickness has almost twice as much impact as depth on the safety factor minimum. As before, the lower radius is negatively correlated. It also has a fair amount of influence, but inversely. And for angle, this blue bar corresponds to the flat curves we saw on previous charts, showing that angle is neutral, with very little impact at all. Now, for the solid mass output, all of the sensitivities are positive, with depth having the most impact. In particular, I noticed that the lower radius has a positive correlation with solid mass. As the radius increases, the mass increases. But it has a negative correlation with safety factor minimum. As the radius increases, the safety factor decreases. Since both of these are contrary to my purpose, I know I'll want to keep the lower radius of the hook as small as possible, although there may be some constraint on how small the radius can be while still having a functional hook. These videos have demonstrated How to use a response surface to do a design exploration of a hook. In Part 1, we set up and generated a response surface. In Part 2, we reviewed the min-max search, goodness of fit, and response chart results. And finally, in Part 3, we interpreted response surface sensitivity results in the local sensitivity curves chart and the local sensitivity chart. This concludes the series, Using Response Surfaces in DesignXplorer.